Okay, I'll go ahead and start, and people can join in the meantime. Good afternoon, everyone. I would like to welcome you all to our second webinar of Rural Equitable and Accessible Transportation, READ Center. My name is Eren Erman Özgüven. I'm an associate professor of Civil and Environmental Engineering at FAMU FSU College of Engineering, and I am also the associate director of our center. Our second webinar this year is about some topic that you would like a lot, I believe. The name of our webinar is Artificial Intelligence and Rural Transportation Network Resilience Against Disasters. So this is very timely that we are looking into disaster resilience using artificial intelligence. We have three speakers today. We have our keynote speaker, Alican Karaer, Dr. Alican Karaer, who is one of our own, a graduate of our department, who is also working as an associate data scientist at ITERIS. And he has been involved in multiple state, federal, international funded research projects. And we really would like to hear from him more about his thoughts on the use of artificial intelligence in the transportation domain. We will also have two other speakers, Richard Anti and Samuel Tachi, that who will talk about their research work in the related to artificial intelligence and transportation engineering with a specific focus on disaster resilience. They are both graduate students of our center here at FAMU FSU College of Engineering. So a couple of housekeeping items. You are all muted at this point. What we're gonna do is, if you have any questions, we will ask you to type them in the chat box, and then I will basically read them to the speaker at the end of his presentation. And we will hopefully have time for a couple of questions that speakers can answer here. If not, we're gonna let them email you, hopefully, with the answers that you're looking for. So with that, I do not want to delay this further. Dr. Alican Karaer is our keynote speaker. Please, Dr. Alican Karaer, introduce yourself, and also we are really happy to have you here joining us. Not just because you're one of our own, but you're one of the prominent young researchers and practitioners in the field. We are happy to have you here.
Thank you, Dr. Özgüven. I'm happy to be here as well. Let me share my screen, and I'll have this on the full screen first, and then I will start. Okay, now it'll work this way. I'll first share the screen on screen 2. Let's share, and then go for it. Okay. I believe you can hear me well. You can see the screen. All is well. Okay, perfect. Good afternoon, good morning, everyone, wherever you're joining to this beautiful and timely webinar. My name is Alican Karaer. I'm a data scientist at ITERIS, a transportation technology company. I'm very honored to be here. As Dr. Özgüven mentioned, I am a graduate from FAMU FSU College of Engineering. And today's topic is very timely as we are expecting a hurricane coming over on our way in the Caribbean. And we're going to talk about AI and rural transportation resilience today. Before I go in, I want to provide some background about myself. I have degrees in civil engineering, emphasizing transportation. I have learned from the best as my Dr. Özgüven was my PhD advisor, and I did my master's with Dr. Tobias Sando. I think he's also here today. And besides that, I've worked with the best as well as one of the directors of these READ centers, Dr. Kidando and Dr. Kitali, was my lab friends during my master's and PhD. I have committed involvement in professional organizations. I have involved in conference organizations and such. I have a strong background in transportation data analytics, implementing data analytics strategies and AI strategies into transportation. And I've been doing industrial research focusing on data field product development with Iteris. My research has been involved mainly on image processing and using AI in transportation. As you've seen, we have done some hurricane impact analysis using before and after satellite images, and we have done some drone work using AI, implementing AI. We have developed some inventories for Department of Transportation, and these studies have been advanced much more with Richard and Samuel. They're going to also talk today. And on the right side, you see one of my last work with Iteris that we have been working on intersection safety. And in fact, we have submitted provisional patent for this work. It's basically do a network screening for intersections in a large network. So with that, I want to go into start with so today I'm going to talk about a little bit of artificial intelligence, and then I will talk about rural transportation, and then I'll go into AI applications for rural transportation resilience. So let's go dive into artificial intelligence. So what is AI? I think AI is doing the dishes because everybody has their own way of doing the dishes. Just like that, AI has already involved in our life, just like doing the dishes. Whether we take a picture through our phone, whether we drive our car, just use one of the streaming platforms that they are suggesting you what do you like. They already know what we like. So just like we all do our dishes differently, AI adapts to our individual needs, making everyday tasks simpler in unique ways. So that's why I think it's a good analogy. Doing the dishes is a good analogy to explain AI today. There are some buzzwords that I will briefly explain, give some methodological explanations of these buzzwords just before we delve into how AI can be implemented into rural transportation resilience. So as you see, artificial intelligence covers machine learning. Machine learning covers deep learning, supervised learning, reinforced, all other different learning. But the main part is machine learning covers deep learning, and deep learning covers the generative AI part, which includes transformers, autoencoders, and generative adversarial networks. So the main advancement of artificial intelligence is the predictive model development. So using a random forest or other different architectures of machine learning has very good performance on developing predictive model development. And deep neural networks implement a similar methodology that how our brain works with neurons and edges, where every edge has a weight, and throughout the training that's called gradient descent. Throughout the training, with a very grady advancement, the error of the prediction goes lower, and when it's minimum, that's what we call the model has been trained. One step further is the convolutional neural network. It's still in the deep learning environment. This is basically for image recognition, object detection, and such, because the system works as has been with the remote sensing for many years. That if you want to detect the vertical object in an image, we could have used this kind of matrix right over here with ones and -1, so that we can highlight the vertical object. So throughout the convolutional neural network, we train this kind of matrices just to get the weight and determine what is in the image. And with autoencoders and transformers, these are the networks that can extract features from the inputs. The input can be an image, or the input can be sound. And further in the transformer, the encoder part can get multiple inputs and generate this to a different object, like for example, lip sync images. And this should sound familiar to you through ChatGPT, because writing ChatGPT is also a transformer, as GPT stands for Generative Pre-trained Transformer. So that's all I want to give as a methodology of the the buzzwords, just to let you know what it does and what it basically means. Very short version. I also want to mention the recent AI developments in transportation. So main thing I want to talk is the ARPA-I. ARPA-I has developed in 2023 by US DOT. It's Advanced Research Projects Agency for Infrastructure. So Advanced Research Project Agency has been developed before for defense, maybe like 15, 20 years ago. It's called DARPA, Defense Advanced Research Project Agency. And ARPA-E was for ARPA Energy. So following these steps, US DOT has launched this new agency to fund high risk, high reward, next generation transportation technologies. And the reason for that one is the problem, as you see in the chart here, the underinvestment in transportation research and development. So as you see in the health and energy, the research and development budget is very high, but in transportation, you see that the research and development budget is very low. And this is presented by US DOT on March 30, 2023, for the discussion with the President Council for Science and Technology at the White House. In addition to that, it also was mentioned that the industry throughout this presentation at the White House, Dr. Robert Hampshire is the DOT Deputy Secretary for Science and Technology. He mentioned that industry invests 50 times more in the vehicles than the infrastructure where those vehicles operate. So to develop those advanced the driving assistance system, for example, automated braking or different detection system, the industry, the auto manufacturers, they invest 50 times more than how much invested to the infrastructure itself. And you can imagine the gap, that it's 50 times more, but it's not because the vehicles are more expensive than the infrastructure. The infrastructure value 5 times more than all the vehicles in the US. So you can imagine the gap, and you can imagine how a great time to be a transportation data scientist to do the research and development work for the infrastructure. Another thing I want to mention is that there was a great report has been published by the NCHRP. It's implementing machine learning at State Department of Transportation. It's a step-by-step roadmap to build agency machine learning capabilities. And another thing I want to mention is that the immediate past president of Federal Highway Administration, Shailen Bhatt, has very recently delivered a keynote speech at the ITS America World Congress in Dubai. There are certain things that I think it's worth mentioning. One of them is that he's a firm believer that within our lifetime, we can use technology and artificial intelligence as key tools to achieve our objective, goal zero injuries and fatalities worldwide. In 2022, there were more than 43,514 fatalities exactly in the United States. And this trend has been growing in the United States, more than 40,000 fatalities in 1 year. This is maybe like a little bit more than 10% of the entire population. So it's like a bleeding edge in the United States. So an artificial intelligence and this kind of investment for the R&D, it could be the solution. Another thing I want to mention is that he said that I have never been somebody who says, let's use technology for the sake of technology. Let's use technology as a tool to achieve better for. So it's never to use AI just because it's cool. It's just to use it for its advancement. So with that, I want to continue. These are the recent AI developments in transportation that I wanted to mention. I want to a little bit mention about the rural transportation as well, to explain how rural and urban transportation has been categorized in the context. Another report from NCHRP developed this figure, just mentioning different states and different reports, providing which type of classifications. So, for example, in Florida, you can see the natural and rural are different. That's been called C1 and C2. Natural is C1; it's like no residential area; it's all natural. But a little bit of a few houses, it's rural. And there is a rural town that's called C2, C2T, and so on and so forth. I think it's great to know like what are the differences of rural and different residential areas and how the transportation has been classified, as well as how the transportation and driving behaviors differs. Another classification is from Department of Agriculture. They just classified all the counties in the United States with metro and non-metro areas. They have a threshold of 5,000 for the population, so lower than 5,000 has been classified as rural, and this threshold has been recently changed in 2013 they used 2,500 as a threshold, but starting from 2023, 5,000 population has been used to develop this classification. From Bureau of Transportation Statistics, there are some statistics for rural areas. For example, 19% of Americans live in rural areas, but 68% of our nation's total lane miles are in rural areas. So we can see the difference. Urban areas, it's 1,056 lane miles per 100,000 residents, but in rural areas, there are almost 10,000 lane miles per 10,000 for 100,000 residents. You can see that there are much more infrastructure in the rural areas. Fatality rate per 100 million vehicle miles traveled is almost 2 times greater in the rural areas. So there are more fatalities proportional to the driving. In rural areas, there are 1.84 fatalities for this much miles traveled compared to 1.08 fatalities in urban areas. And 43% of highway fatalities occur on rural roads. As you can see, the total numbers of the total fatalities. And 46% of truck vehicle miles traveled occurred in rural areas, so almost half. But this is an interesting statistics. So when a bridge closes, how much you need to travel to detour just to pass through that bridge. So in rural areas, that detour is 17.1 miles, but in urban areas is 9.78 miles. So 2 times longer in rural compared to the urban areas. And these are the number of closed and posted bridges in rural areas. Just some statistics to give you understanding of how rural transportation differs from urban transportation. And I want to mention about the challenges as well, how rural transportation, what are the challenges of the rural transportation? So there, I found 2 reports from TRIP, National Transportation Research Nonprofit. The left one is published in May 2020, Rural Connection, Challenges and Opportunities in American Heartland. And there is the right one is very recently published in this very month, Rural Connections, Examining the Safety, Connectivity, Connections. In this report, rural transportation challenges are very explicitly shared. So I'm gonna a little bit summarize of the challenges over here. So there are 3 main challenges of rural transportation: funding, safety, and connectivity. So according to the report, there are almost $200 billion the backlog budget to perform the required maintenance of the rural transportation infrastructure. And for safety, as I mentioned before, there are much more fatalities in the rural areas. And the reasoning for that one is explained in the report as a lack of desirable roadway safety features. These are the signing and pavement markings and such. Longer emergency vehicle response times. This is also related to accessibility and connectivity. And there is also higher speeding rates. So the speeding behaviors are much more common in rural areas. And for connectivity, rural area residents often must travel longer distances to access health services, education, employment, and socializing. The U.S. interstate system was also designed in almost 50 years ago. 70 years ago, in 1956. The population has more than doubled since then. So there could be some more needs, and this could be one of the challenges of the rural transportation. Rural transportation resilience. So rural communities are often the most vulnerable when the disaster strikes. This is we need to face this fact. Whether it's floods, wildfires, hurricanes, or landslides, these are typically have fewer. The rural areas typically have fewer resources, longer evacuation times, and limited access to robust infrastructure compared to urban centers. Strengthening the resilience of transportation networks in these regions is not just a matter of convenience because of these challenges. It is a matter of safety and surveillance. So that's why this is where the AI comes in. What type of solutions can be generated through AI? Let's elaborate that on. I have some scenarios that what we can do using AI. For example, predictive analysis. As I mentioned, AI through machine learning, deep learning, had a very strong side on developing predictive models. So AI can analyze historical data, weather patterns, geographical information, and estimate the impact of disasters on rural transportation network. For instance, transportation agencies can simulate potential flood scenarios using AI to identify which roads or bridges are most vulnerable. And using that analysis, infrastructure maintenance budgets are very limited, and AI's ability to help prioritize where to allocate resources can make a huge difference in ensuring that critical transportation roads remain operational during and after the disasters. This allows them to take action in advance, whether by reinforcing weak spots or positioning emergency resources. Another use case could be real-time data and decision-making. So disasters are dynamic and conditions can change rapidly. So AI's ability to process and analyze real-time data can help transportation agencies respond more effectively as the disaster is still ongoing. So rural areas are often lack the dense sensor networks found in cities. So the available sensors may not be enough to make the best decision. Advancement in satellite technology, drones, and even social media provide valuable data sources. Imagine a scenario where wildfire is rapidly spreading in a rural area. So with AI, decision makers can analyze satellite images to predict which roads will be cut off next, allowing them to reroute traffic and ensure that evacuation plans remain effective, even as the situation evolves. So AI can aggregate and analyze these various data streams to assess road conditions, identify passable roads, and optimize evacuation strategies in real time. Another use case is specifically for the isolated areas, maybe classified as nature. These rural transportation networks are often very sparse, so we have those areas. When a disaster hits, these communities can be completely cut off, lacking access to essential services such as medical or even just food. So AI-powered optimization algorithms can help by identifying the most critical roads that needs to be cleared or repaired first. So this is aftermath of a disaster. It's as important as the preparation process or during the disaster. For instance, if a rural town is cut off by a landslide, AI can simulate different recovery scenarios and prioritize clearing the roads that are essential for emergency services and supply deliveries. This ensures that rural communities can regain access more quickly, minimizing isolation and helping to accelerate recovery efforts. Another scenario for using AI in rural transportation is the post-disaster infrastructure assessment. We have done a study with that using satellite images, not specifically involving AI per se, but this was using satellite images before and after and analyzing the impact in the city through vegetative debris. So once the immediate danger has passed, one of the biggest challenges in rural areas is assessing the condition of the transportation infrastructure. Sending crews to manually inspect roads and bridges can be time-consuming and very dangerous. So drones equipped with AI-driven image recognition can fly over affected areas and quickly identify damages to roads or bridges, rail lines, or power lines as well. By providing real-time assessments of infrastructure damage, AI allows agencies to begin repairs sooner and focus on the areas that need attention the most. And this was one of the goals in our published study as well. The goal was determining the most critical area. Another and last but not the least is the equity. Rural areas, particularly those with low income population, are often disproportionately affected by disasters. So we have seen this in Hurricane Katrina. I think it's the most famous one with the disproportionate impact on different side of population. So AI models can analyze demographic data alongside disaster impact simulations, allowing agencies to understand which populations are at the greatest risk and tailor their response accordingly. And here there is a study that involving vulnerability and people with the demographic data. This ensures that the rural communities receive the resources they need to recover, regardless of their economic standing or geographic location. So with that, I'd like to conclude my presentation with AI has the potential to revolutionize how we think about disaster resilience, especially in rural areas. From predictive analysis and real-time decision-making to rapid infrastructure assessment and equitable recovery efforts, AI provides new tools to strengthen rural transportation networks and ensure that these communities remain connected and supported in times of crisis. It's important to remember that while AI is a powerful tool, it is only as effective as the human decision guiding its use. Our goal should always be to leverage technology in ways that make a tangible, positive difference in the lives of those who are the most vulnerable. So with that, I'd like to thank you again, and I'll be happy to answer if you have any question, or I don't know, Dr. Özgüven, if you'd like to go to the next speaker and answer the questions at the very last.
Thank you very much, Alican. This was a very refreshing presentation.
Mm-hmm.
As we see, there are a lot of possibilities here, and there are so many challenges, obviously, but companies like yours and universities like academia, like our side, we have been kind of trying to work on them. So for those of you that have joined later, if you have any questions, please write it in the chat box. And I can read it to Alican so that he can answer them. But in the meantime, let me start with a question, Alican, myself. How do you see the role of both your side and our side working together to find solutions here? I know there are so many different projects on both sides. There are partnerships here and there. But what do you think would be the best way of working together?
I think it's start with the problem. The problem is especially where we live in the Panhandle area. In this area, it's the hurricane region. So we have a lot of disasters, and this is already estimated when it's going to come. So our goal, whether which side, industry or the academia, our goal is always to provide solutions and have our transportation network as efficient as possible. I think the best way to work is just set this goal to the main side, and then come up with the bureaucracy side and other sides as quickly as possible, so that I think the main issue with this kind of collaborations is the bureaucracy part. As fast as we can go through this brokerage side, we can find the best solutions.
Yeah, that's a very good point. That's a very good point. We are all eager to solve these challenges, but there is always the paperwork associated with it, and for these partnerships to happen, you need to solve all those political, bottlenecks. That's a very good point. I don't see any other questions, Alican. So I would like to thank you again joining us today in your busy schedule and serving as our keynote speaker. From here on, we're gonna go to Richard Anti. So Richard is a PhD candidate, and he has been working on many different projects related to artificial intelligence funded by external agencies. As Alican was saying, we had projects that he started working on, and Richard and Samuel took over from him, and we kind of, as a result, published a couple of papers and reports. But with that being said, Richard, please go ahead and introduce yourself, and floor is yours.
Hi, everyone. My name is Richard, and I'm a graduate assistant at the Reed Center. And I'm also a PhD student, and my research is mostly in disaster resilience and also AI applications in roadway geometry data collection. So today, I will briefly talk about a few case studies that we have carried out in the Florida area. Okay. So, all right. So the first case study is one that has to do with using satellite images to assess disaster debris on the roadways after hurricanes and tornadoes occur. And so the objectives of this study was to develop an integrated GIS and image processing approach, and also perform a macro-level disaster debris assessment using open source satellite images. And the goals here were to develop the GIS framework to extract NDVI changes, apply the framework to identify and extract the roadway segments that were severely affected by these disasters, and also evaluate their performance with ground truth data. So in the first study, the target was Hurricane Michael. And when Hurricane Michael struck Calhoun County, it caused a lot of destruction to the county, to their roadways. And so in this study, we use Sentinel-2 imagery to extract and assess the damages that occurred in the county. And in this particular study, there were two analyses that were performed. The first one was for the entire county, and then the second one was just for the roadways. And so the study used time periods, a shorter time period for the roadways, and then a longer time period for the entire county. And the roadways were as a result of understanding which areas that were highly impacted by the debris. And so if you want to inform agencies and emergency operation people where to visit first and help the roadways to resume its regular operations. So here is the results for the first analysis, which had to do with the entire county. From the results, the northeastern part of the county had a lot of damages, and they were highly affected by the hurricane. And also from the second analysis, we classified the roadways that were affected. We segmented the roadways, classified them, and some were classified under very high, from very high to very low. And the roadway 69C was the roadway that was highly affected and impacted by the presence of the hurricane. And so after the study, we also compared it to the hurricane path. And indeed, these were the areas that were highly affected, the northeastern parts of the county, and the roadways that were also affected were found in that area. And that area also of the county was where we had cities like Arthur and Blountstown, which were also the most populated area in the county. Now, with the second analysis, a tornado occurred here in Tallahassee, Leon County, somewhere in April. So we used a similar method, but here we used a higher resolution image, which was a 3-meter satellite image, and also a slightly different methodology from the previous analysis that we did. And here, we also found out that the debris from the tornado occurrence was really high. It affected the county a lot, affected so many areas. There were power outages for several days, and these were the roadways that were highly affected. These roadways were so much affected, and there was one particular roadway which is on Capital Circle, and it was it had a very high debris accumulation level over there. Now, similarly, this roadways were also classified as well, and the results was also compared to the damage points and also the tornado track. So we can see over here the damage points and the tornado track, and this particular framework that we designed was 75% accurate. Now, with the second case study, the idea was to use AI and aerial imagery to extract roadway geometry data from for several roadway analysis and safety studies. And so here, the objective of this study was to develop an automated YOLO-based extraction algorithm to identify and extract roadway geometry data, such as bicycles and turning lane configurations. And here, what we did was to develop 2 multi-class detection models, which are based on YOLO, and evaluate the performance of these models with the ground truth data, and apply the model to also extract features in Florida roadways. Now, here is a brief description of the data and the pre-processing steps that were used here. Since the images that we obtained are very high resolution, we had to pre-process them to make it easier to work with and handle. And so an automated Maxent model was used to extract the areas of interest, just the roadways, and then use that data to create our training data, and further also use it for our detection as well. So these are the 2 models that were created. One was a 4-class model, which was for the turning lane, the left, right, center. And then we also had a non-class, and we had the bicycle lane model as well. So these models were detecting the features within those lanes to help us identify those lanes for several safety analysis. And here is the data distribution for training the model. The left only was 30%, right was about 30 as well, center lane was 14, and then the non-class was 27. The non-class was made up of all the other features which were not left, right, and center. And this helps the model to differentiate and distinguish between the features of interest and those that are not of interest. And for the bicycle lane, it was a single class model. So yes, so this is a brief description of how the turning lane detector works. So it's based on the YOLO, and also the YOLO, just like Dr. Karia said, it's really good for object detection, object tracking, and its architecture is such that it's made up of a backbone, a neck, and then a head. And it also performs detections in 3 stages. And these stages help the model to detect even very, very small features. So comparing it to other models like the RCNN and the other deep learning models, we chose and went with YOLO, and YOLO also works faster as well. So that was another advantage for selecting it. Now here is the model training parameters. So here we can see the confidence and the precision curve, and we also see the precision and recall curve as well. So with the precision and recall curve, it basically shows describes the sensitivity of the model in detecting true positives, and also the precision as well, how well the model predicts those positive values. So you always want your curve to be on this corner, the corner right. So that way you have very high precision and very high recall. And this was for the left, right, center model. And here's the bicycle lane model. And for the precision and confidence curve as well, you also want your curve to be on this corner, because you want the model to be able to precisely detect true positives, even at the lowest confidence level as possible. So this is how they look like. And then the average accuracy of the two models, the turning lane was 0.98 and the bicycle lane was 0.95. Now, after the models were created, where we went ahead to use the model to detect features on the roadways. And so first we tried single images to see how it works. And now after the model that performs this detection, it draws bounding boxes around those features of interest. And since the images were also very high resolution images and very large size, we had to also implement a stepwise detection method where the images were split into smaller chips, and then the detections occur on those smaller chips, and then afterwards we put everything together into one to create the inventory. So this is basically how the detections were performed. And here are some examples of the turning lane feature detection images. And here we can see some left lanes and right lanes as well. And here are some examples for the bicycle features as well. So after the model was trained, we also did a second step, that was to check the model's evaluation and how it performs on entirely new data. So we created a ground truth data of Leon County, and we used that to check the model's performance. So based on the true positives, the false negatives, and the false positives. So these are basically some of the results that we obtained. And the average F1, which was a metric that balances both precision and then accuracy, was 88% for the turning lane model, and it was 85% for the bicycle lane model. So here is also the coefficient metrics for both models. Here we see the how the turning lane model perform on the ground truth data. And then this is how the bicycle lane also performs on the ground truth data as well. Now, the model was further used to also detect the features in Leon County, and then a map was created in that regard. So the study aimed at developing an automated roadway geometry data extraction model based on the high resolution images to identify these turning features. And indeed, this is an innovative solution which will replace these traditional methods, which are very labor intensive and also prone to errors as well. And with future studies, we are looking at detecting most of these other features that we have. We have left through, right through, center, rail, crossings, and all the other features that we see. So that will be the future study for this particular project. Thank you.
Thank you, Richard. So this is important, especially for rural areas where some of these databases are not available. So that's important, especially for rural counties and cities. I do not see any questions at this point for you, Richard. From there, I would like to ask Samuel. So Samuel also has been working in the project that is funded by Reed Center, focusing on artificial intelligence and disaster resilience. So Samuel, please go ahead.
Good afternoon, everyone. My name is Samuel Tachi. I'm a civil engineering PhD candidate at the Civil Engineering Department, and also a research assistant at the Reed Center. My research has been focused on assessing.
Comrade, did you share your screen, please?
Thank you, Prof. Yes, so my research has been focused on assessing the spatial accessibility of rural counties within Florida to critical facilities such as shelters, hospitals, libraries, and etc. And also, I've also been focused on using machine learning to assess the impact of hurricanes on roadways. Now, with today's presentation, I'll be focusing on assessing the impact of hurricanes on roadway closures and accessibility, a machine learning case study with focus on 2 hurricanes, Idalia and then Hurricane Ian. My presentation today will stem from the introduction, from the problem statement, objective methodology, straight to the conclusions and limitations. Now, when we talk about hurricanes and other weather-related events, they have caused extensive damage to a lot of infrastructure in Florida, with focus on some of our bridges, our roadways, and some of the tunnels. Now, the US have spent a lot of money on the damages caused by hurricanes. Within the span of 45 years, the US spent over $2 trillion in hurricane-induced damages. And this calls for the need to assess the damages that are caused by hurricanes in order for us to mitigate some of these adverse effects. My problem statement: when hurricanes occur or when natural disasters occur, it causes significant damage to our roadway infrastructure. And then when it happens, there is a need for us to assess the impact caused by these hurricanes, because there are a lot of roadways that are closed. And when they are closed, it impacts productivity and everything we do. So the research I'm doing was with a focus to assess the impact of the hurricanes on the roadways after they happen, so that it can create an efficient reconstruction process after the event. Now, these disruptions also, when they happen, they cause profound economic and then societal consequences, which makes it very imperative to assess and then mitigate their impact effectively. Also, there have been traditional methods of assessing these roadway impacts when hurricanes occur. Sometimes they use manual labeling. Sometimes we have skilled people who go to the field to analyze and assess the whole situation. These are labor intensive, and then there are errors that comes with when humans go to assess these features. So the aim of the research was to develop a machine learning model with the use of a high-resolution satellite imagery, which was provided by the National Hurricane Center, to assess the impact by developing a model that can classify the roadways into open, partially closed, and then fully closed. Now, with this, we are able to assess the extent and spatial distribution of the closure of the roads, which are caused by the hurricanes. Also, we are able to identify vulnerable locations and then evaluate how resilient some of the roadways infrastructures can be with respect to hurricanes-induced disruptions. And then the objective is also to provide insights for planners, engineers, and policymakers as to how we can manage our counties and then the places that are prone to hurricanes, and then find recovery and disaster recovery efforts, and then also find ways to effectively evacuate people during hurricane events. The data that was used was high-resolution imagery, like I said before, from National Hurricane Center. I used demographic data sets and also some roadway shape files from FDOT's website. Talking about Hurricane Ian was a Category 4 hurricane and one of the biggest to hit Florida. Even in the US history, it was one of the biggest to hit the United States. It happened in Lee County, Florida over here in 2022. It was one of the strongest, even as compared to Hurricane Michael in 2018. We also have Hurricane Idalia, which was also considered in this study, which was a Category 3 hurricane, which made landfall in Northwest Florida in 2022. I'll move on to the methodology. With this research, we developed the machine learning model. So the machine learning model started from data collection and preparation, moved to data preprocessing, where image sampling, image segmentation, and image classification was performed. Training data was also prepared after all these methods were done, and then a roadway extraction model was developed before the detection model, and then finally the detections were analyzed to find places that were more impacted. With the sampling, I compared the post-hurricane and the pre-hurricane image to make sure they have the same resolution. So a nearest neighbor method was used to adjust the post-hurricane imagery to the pre-hurricane imagery. And after that, image segmentation was done to analyze and evaluate the details of the image. So this was done to understand the details that were in the image, the buildings, the roadways, vegetation, and everything that was done. And the main features that were compared in this image over here were the roadways and the buildings, because those were the main infrastructures being considered. Now, after that, image classification was done using a support, using a random forest classifier. There are other machine learning models that can be used to classify the image, support vector machine, maximum likelihood. But in our case, a random forest classifier was developed to also classify the images. Now, the classification was done to clearly indicate every particular feature that was in the image, as to whether roadways, water bodies, vegetations, buildings. I assigned colors to them so that we can know the distinct features that were in the image. Now, after the images were classified, the roadways were extracted, and then the training data was also prepared to start the detection model development. Now, with the roadway extraction model, a multi-task roadway extraction model was used, and this uses a center line extraction where I input the center line of the roadways into the model and then buffer it by certain feet to make sure that just the roadways are extracted. And it uses a UNet backbone for this extraction. This was the metrics of the roadway extraction model. These were some of the results, and then this was the loss graph to indicate the performance of the model. After that, the main machine learning detection model was developed to detect the roadways into several classes, which were open classes, partially classes, and then fully closed. Now, 600 images were manually trained with bounding boxes, and then 40% of those 600 images were open classes, 30% were partially closed classes, and then another 30% was fully closed classes. Now, this was the model which uses the YOLO V3 network architecture, where we input some images, and then the images, within those images, they are divided into grids and then pixels. And then there is a feature extraction which uses the ResNet backbone to extract certain features from the images that were put inside the model. After that, a detector was also used to detect each of the images, and then this uses a residual block to classify them, and then within the detector, it detects them based on 3 scales. It could be as 32 by 32, 16 by 16, and 8 by 8. It uses the 3 prediction scales. And then after that, the bounding boxes classifies them into as to whether they are open, they are closed, fully closed, or they are partially closed. This was the result of the detection model. We have the ground truth against the prediction results, and then this is the loss graph for the detection model. Now, we used 80% training data set and then 20% for the test and validation. But here are some of the results of the detections for Hurricane Ian. And we use these performance metrics, the recall, the precision, and the R1 score, F1 score to evaluate the model's performance and the detection results. So these were the general detection results. We had 110 open roadways, 55 fully closed roadways and then 96 partially closed roadways. Now, these are the confusion metrics for the which maps the actual class against the predicted class over here, and which you can see we have the open, fully closed, and partially closed. And over here are the performance metrics where we have the true positive, the false positive, and the false negative. And also these are the precision recall and F1 scores, which were used to assess the model performance. And they are in percentages, as we can see over here. Now, after the detection was done, what I did was to classify the detections into the various areas in Southwest Florida for Hurricane Ian. Now, over here, we have most of the roads that were affected based on the detection. There were a lot of closed roads over here. Over here, there were less over here, which were moderately affected. There were heavily affected roads over here because we detected a lot of fully closed roads over here. Also over here, we detected a lot of flooded roads, and over here, we had a lot of fully closed and partially closed roadways over here. Now, after classifying them into moderately closed, heavily closed over here, what we did is that we looked at the population data set, the demographic data set, and then we mapped them. Over here, it was seen that there were a lot of people that were residing in this part of the county, and over here too, there were a lot of people who resided. Now over here, we didn't have a lot of people residing over here, but when you check over here, there were a lot of people residing over here, but it wasn't all that affected. But when we look over here, there are a lot of people who are residing over here. The population over here was very high, and the place was mostly affected by flood. And this place was mostly coastal. It was prone to a lot of flooding. But when we look at this part, which was the St. James area, it was heavily affected, but there were not a lot of people residing in the area. That is for total population. When you look here, I did same for aged population, which is people age 65 and above. The model was also applied to Hurricane Idalia, and these were some of the performances of the model in Hurricane Idalia, which happened in Northwest Florida. So the model was applied to two separate places in Florida, Southwest and then Northwest of Florida. And these are some of the detections that we got from Hurricane Idalia based on the same model. Now, the findings clearly indicates that the model is able to detect roadways regardless of wherever they are located, because we applied the model in two separate places, Southwest of Florida and Northwest of Florida. So we're able to detect for both areas, and some of the conclusions we got from the whole research was that the study is able to detect the models regardless, it was able to detect roadway conditions regardless of wherever they are located. And this clearly shows that in the context of roadway closure and accessibility, machine learning performs better and then very efficient and effective than sending people to the field, whereby we put the people at risk, and also there are errors that we cannot clearly identify. There were some limitations of the study. During the detection, there were a lot of occlusions as a result of debris on the road, and also classifying the roads. Sometimes it becomes very challenging because you look at the extent of the damage to classify the roads, whether they are partial or they are fully closed. And then also we're looking at the visibility, which I talked about, occlusion from trees. Some of the trees were shaded on the road, so the model detected some of them as the road being closed. Meanwhile, they were not closed, but they were being occluded by trees which were on the roadside. Now, when we look into the future, I'm extending this study by developing roadway vulnerability index and then roadway condition impact index to be able to classify various roadways as to whether they are vulnerable or they are not vulnerable. And then this can be done by considering two hurricanes that happen within the same location. Thank you very much.
Thank you so much. Again, an excellent application that has been done by two students you have seen in his last presentations. With that, we are at 2 p.m. mark, and I'm not seeing any questions in the chat box. So first, I would like to thank the speakers today, Dr. Alican Karayer and Mr. Ante and Mr. Tachi, thank you very much again sharing your research with us today. We hope to share more of our results in the upcoming months and possibly in different domains like TRB, Transportation Research Board Conference. I would like to, in the meantime, thank Dr. Ramoses, our center director. Samuel, you can close your share. Turn off, please. I would like to thank Dr. Ramoses, our director, and Dr. Segai Edego and Imon Bryant for making this webinar happen. We're going to have our next webinar on September 25th. And if you are interested, then please join us in that webinar too. And with that, especially for those of you that are in Florida, I would like to say stay safe. The hurricane is on its way, it seems. We'll see if we're going to be affected. But again, good luck and stay safe. So thank you very much for all joining today. And see you all in our next webinar.